Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Hello students, welcome to this session. In this session I am going to start with the introduction of geometry design for roadways, but before that I need to solve some problems related to the highway alignment which was discussed in the last session. So in the last session we have talked about the highway alignment. Highway alignment is nothing but marking the center line of the road, and in order to finalize the alignment and to mark the center line of the road, we need to carry out different engineering surveys which we have seen already in the last session, like map study, reconnaissance, preliminary survey, final and detailed survey. And for finalizing the alignment, one of the technique what we have discussed is with OD survey, the right origin destination survey. Means we are drawing the desired lines, and from the desired lines we have identified the final alignment. Now, as I said, there itself there are many other techniques like benefit to cost ratio, net present value method. Similarly, we have one more concept for finalizing the alignment, that is concept of saturation system. This is one of the systems that can be used for finalizing the alignment. So, as I already discussed in the last session, that there might be number of routes that are possible from A to B, and for example, let us say there are three routes here: route number 1, route number 2, and route number 3. And say route number 1 is 100 kilometers, route number 2 is say 70 kilometers, route number 3 is say 120 kilometers. Now, in 100 kilometers of the journey, or in 70 kilometers of the journey, or in this 120 kilometers of journey, there will be number of villages that will be connected to you. And I said in my first session that the major problem with the villages is connectivity. We need to connect them. We need to connect the villages. So we will be connecting the villages on those roads, and we have got this many routes here. For example, if you construct route number 1, say some 40 villages are getting connected. Say 20 villages are getting connected, and say 30 villages are getting connected here. Now, I said that 40 villages are getting connected, or 20 villages, or 30 villages are getting connected. Who will be connected in that villages, ma? Who will be connected in those villages? Who will be using that particular roads? Yeah. So all these concepts of saturation system talks about those two elements. Who are the advantages or the elements of those villages? So this concept of saturation system has two major factors that are also related with the villages itself. So if you construct this road, route number 1, 40 villages are getting connected, and villages can have different number of people in it, right? So those people will be getting benefited. So the people or the population which are being connected will get benefited. And as I already said that villages are meant for agriculture, and from the agriculture people will grow some things, and that things will be given as an input for many of the industries. So there will be exchange of goods happening from the villages to the industries. Again, from the industries, the final product will be reaching to those villages as a product. So agricultural and industrial productivity. These two are the happenings that will be there in the village. And if you construct a road, these two elements will be the major criteria for it. Now, what we'll be doing in this concept of saturation system is we need to assign utility factors. These are nothing but constants. And these utility factors can be assigned randomly. There are no hard and fast rules for assigning these utility factors, and it is completely random. And it is when you are assigning, or when you are deciding this utility factors, a small logic is to be followed. That's it. Small logic is to be followed, and that is nothing but if the population is more, then utility factor should be more. Utility factor should be more. That's it. That's it. For example, there are two villages. First village has a population of say 1000. Second village has a population of say 300. Okay. Two villages are there. First village with a population of 1000. Second village with a population of 100. Now, for example, for the first village, I say that utility factor is 1. Let us take the utility factor as constant as 1. Now, the only small logic that is to be followed is, as the second village has a population of less than 1000, that is, I have given the second village as a population of only 300. So the utility factor that is to be taken here should be less than 1. That's it. That's it. You can take anything. You can take 0.1, you can take 0.3, you can take 0.2, you can take 0.5. Whatever it is, you can take. The only logic to be followed is it should be less than 1. Now, for example, if third village comes, if there is one more village that has been considered with a population of say 1500, then what about my utility factor? Your utility factor obviously should be more than 1, because for 1000 you have taken the utility factor as 1. Now the population is 1500, so you can take any value which is more than 1. You can take it as 2, you can take it as 1.5, you can take it as 3. That is up to your wish. That is the one and only simple logic to be considered in the concept of saturation system. And the same is applied for the agricultural or industrial productivity, and generally it is expressed in terms of tons. 1000 tons of vegetables are going, 1000 tons of sugarcane is going, right? So expressed in terms of tons. So the more is the number of tons, the more will be the usage, the more will be the utility value. That's it. That's it. So with this little concept, let us solve a problem given in your workbook. So I'll be reading out the question for you. The problem number 1 of your workbook, highway alignment. 3 new roads PQR are planned in a district. So 3 new roads are planned in a district. PQR are planned in a district. The data for the 3 roads are given in the table below. So there is a table given below. And based on the principle of maximum utility, so this concept of saturation system is also called as concept of maximum utility system. Okay. So based on the principle of maximum utility, the order of priority should be what? So the corresponding lengths are also given in the table. So I'm drawing that table here. Lengths, number of villages with population. Less than 2000, 2000 to 5000, and greater than 5000. Right? So road P is of 20 kilometers, road Q is of 28 kilometers, road R is of 12 kilometers. 8, 6, and 1, 19, 8, and 4. And it is 7, 5, 2. Right? So that's the question for us, and we need to suggest the order of priority. Means if you have less resources, which road is to be constructed? Either it is road P or road Q or road R. Which road is to be constructed? Now to decide that, he has given itself that we need to calculate it as per the utility value. So here we have 3 routes, and each route has got different lengths with different villages connected. So what I do is, if I construct a road, some people will be getting benefited, and that's why I'm going to calculate the utility value. So I write it as utility value, right? And how will I get this utility value? First I need to, as I said, first you need to assign the utility factors, constants. That is my first job. So for example, I am assigning a utility factor of say 1 for this. So if a village is having a population which is less than 1000, I am giving the utility factor as 1 for that category. Right? Now, with the simple logic as we discussed in this example, with the small and simple logic as we discussed in this example, now tell me what will be the utility factor for this group of villages with population 2000 to 5000. Will it be less than 1 or more than 1? So if the population is less than 1, you take it as less than 2000, you have considered it as 1. So as the population now is more, I simply take this utility factor, anything which is more than 1. You can take it as 1.5, 5, 10, 100, whatever it is. But for calculating simply, for making my calculation simpler, I take it as 2. Right? And the same reason, the same logic, now I take it as 3. Right? So the utility value for the P is 8 into 1 plus 6 into 2 plus 1 into 3. That is the total utility value. Right? Now, this utility value, what I have calculated, is for 20 kilometers. This many villages are existing for 20 kilometers. And each road is having different lengths. And if you vary the length of the road, the construction cost increases, right? As the length increases, your construction cost is going to increase. So what I do is, I will calculate the utility value per kilometer for comparing. If anybody asks you what is the utility value for road number P, this is the answer. But here you don't want the individual utility values, you want the order of sequence. So you need to compare the roads which are existing, and for its comparison you need to calculate the utility value per kilometer, right? Because each road is having different kilometers. So this much is the utility value, this much is the utility value for 20 kilometers. For 1 kilometer, how much is the utility value? So I divided the total utility value with number of kilometers, that is 20. So if you have calculators, you can solve it. So if you solve it, it comes as 1.15. So the total utility value per kilometer comes as 1.15 for route P. And similarly, you can do it for route Q and route R as well. Come on, do it. So I'm also doing here 19 into 1 plus 8 into 2 plus 4 into 3. That is the total utility value for road Q, but it is of 28 kilometers. So I divide it with number of kilometers. And if you calculate this, it comes as 1.67. Right? And similarly for the last route, 7 into 1 plus 5 into 2 plus 2 into 3 divided by the total kilometers is 12. So if you calculate that, it comes as 1.91. So these are the total utility values for the three routes here, route P, route Q and route R. Now simply he has asked us the order of priority, means if less funding is available, which route should I construct? Obviously I should go for the route which has got the highest utility value, and here the highest utility value you got is for the route R, next is for Q and next is for P, right? So the order of priority here is from these three values, the order of priority is R, Q and P, which is given in the option D, right? So this is how we solve to find the order of priority. So my alignment here is route R, road R. And if further, if I get some more funding, I will go with route Q. And then also if I get some more extra funding, I go for route P, right? So you can note it down this problem as well as that concept. So I hope you're done with the problem, right? So let us start with the basics of the roadways, that is highway geometric design. Yeah. So highway geometric design. It's a completely important topic. Of course, we are not going to start with the geometric design here. We are going to cover the basics of geometric design, which are required for designing the roads. So why we should design our roads? What is the necessity of designing our roads? Simple. We should design our roads to ensure that people travel with maximum speed with reasonable cost and safely. To achieve all these things, we need to properly design our roads to ensure that we travel at maximum speed with less cost and with safety. Now, every part of this geometry design, every element of this geometry design is based on one single element. Everything, every design what we provide on the roads is based on only one element. That is nothing but design speed. Now there are two terms here, design speed and maximum speed. There is a very minute difference between these two terms, design speed and maximum speed. Can anybody differentiate it? Design speed is the maximum speed at which the vehicles can travel safely, right? It is the maximum speed at which vehicles can travel safely. Whereas maximum speed is the at which the vehicle can move. Maximum speed, it is defined as the maximum speed at which the vehicle can move or it can travel. So only term which is differentiating with maximum speed and design term is safety. Safety. Now for a given road, which speed is always constant? Answer would be design speed. Because for a given road, design speed is always constant. If I say that this road is having a design speed of 80 kmph, that means wherever it is, whatever the time is, no matter what type of vehicle moves over it, design speed is always constant. That is 80 kmph for that particular road. But maximum speed varies. Maximum speed varies from person to person, vehicle to vehicle, driver to driver, condition to condition of the driver, right? If you are traveling For a two-wheeler, you will have one maximum speed. If you're traveling with a four-wheeler, your maximum speed will be more. Similarly, from vehicle to vehicle, it varies. From driver to driver, if you're drunk, you can travel, you don't know the condition, right? You are not able to decide what you are doing if you are more drunk. So maximum speed is going to vary from situation to situation, but design speed is always constant for a given road. And if you travel with a speed which is less than or equal to design speed, that means you are safer. You are safer because every geometrical element we provide on the road is provided by considering this design speed, right? That's what design speed is. All the geometrical elements are based on design speed, and this design speed is again influenced by one major criteria, that is topography. Topography. So topography is nothing but terrain conditions and the topography in India can be classified into four categories. A very important one which will be coming for us: plain, rolling, mountainous, and steepy terrain. So that is how topography is being defined as per the four categories: plain, rolling, mountainous, and steepy terrain. So topography here is nothing but slope. Slope can be defined in three formats in transportation engineering. The first format is using theta. So if I use a theta, that means there is a slope, right? There is a rotation, whether it is sine theta or cos theta or tan theta, doesn't matter. If I say if I say theta, that means there is slope, whatever it is. Second way of representing it is 1 in n. 1 in n means n horizontal is to 1 vertical. Means if you move n meters horizontally, the vertical rise is 1 meter. 1 in n. N horizontal is to 1 vertical. So n meters and 1 meters. So there is a slope here. And the third way of representing is percentage format, which is nothing but 1 by n into 100. The same thing, same 1 in n, I have written it as 1 by n into 100. And in transportation engineering, mostly I will be using slope in percentage format. So 1 in n format. So you need to know how to convert 1 in n into percentage, and from percentage to 1 in n formats, which we'll be doing in some of the problems. Okay. So for this, terrain or topography conditions, as I said, it is of four different types: plain, rolling, mountainous, and steepy terrain. So if the slope is in between 0 to 10%, it is called as plain terrain. If the slope is in between 10 to 25%, it is called as rolling terrain. And if it is between 25 to 60%, it is called as mountainous terrain. And if it is more than 60%, it is called as steepy terrain. So that is how we say the terrain of that particular region based on the slope. And this is the very common sense that as the slope increases, your design speed is going to decrease, obviously, right or not? So for plain regions, the design speed will be more. For steepy regions and mountainous regions, the design speed will be lesser. So all the geometrical elements is based on design speed, and design speed is based on topography, right? So we have different types of roads like design national highway, state highway, MDR, ODR, and village roads. And for each type of road, it has got a value of design speed, which is given by IRC, and that is as per this table, which I'm going to write here. So we have different types of roads. As I said that both national highways and state highways come under one category. So I've mentioned in the same national highways and state highway, MDR, ODR, and village roads, right? And this design speed is based on topography, and we have different topographies like plain, rolling, mountainous, and steepy terrains. Again, each topography can be divided into two categories like this way. They can be categorized like this: ruling and minimum. Ruling and minimum. Ruling and minimum. Ruling and minimum. Right? So now I'll be writing those numbers as per the table given or as per the thing mentioned in IRC codebook. So here it is 100, 80, 80 and 65, 50 and 40, and 40 and 30, right? So this is how it has been defined. So if you see in this table in the first line, for both national highways and state highways, the ruling design speed for plain terrain is 100 kmph, and the minimum design speed that should be adopted for national highways and state highways in the plain terrain should be 100 kmph. Everything here is in kmph, ma. All the speeds are in kmph here. Okay. So ruling means maximum. No matter what the situation is, no matter what the condition is, the maximum, the ruling design speed on a national highway or a state highway for plain terrain should not be more than 100. Similarly, no matter what the situation is, no matter what the type of condition is, what the surface is, wherever it is, the minimum design speed that should be considered for a national highway is 80 kmph. That is what this means, ruling and minimum. Ruling means maximum, right? So as we discussed here, as the terrain conditions increases, means as the slope increases, the design speed decreases. You can see here, for national highway, the maximum speed for plain region is 100 kmph. For the same national highway, if you are constructing in a steepy terrain, the design speed is only 40 kmph. So in the same fashion, if you see here, for national highway and state highway, in the plain terrain, it is 100 kmph. Now you are decreasing the quality, means you are coming to a lower category road, that is major district road. So obviously this design speed will not be 100. It will be decreasing, right? So it is 80, 65, 65 and 50, 40, 30 and 30, 20. So these are the design speed for major district roads. And similarly, next one is a much lower category, that is other district roads. So the design speeds which are given in this line will be lesser, right, for ODR. So it starts with 65, 50, 50, 40, 30, 25, and 25, 20. So these are the design speeds for a other district road. And lastly, village road, it is much lesser category. So it is 50, 40, 40, 35, 25, 20, and 25, 20. So this is how we decide the design speed based on IRC, and you can note it down now. Yeah, I hope you are done with this writing part. So we have seen the first geometrical element, that is design speed. So a design speed mainly depends on the topography and the type of road. And for urban areas, we have already seen the design speeds in the types of roads in urban areas like arterial, subarterial, collector, and local streets. There itself, for arterial road, it is 80 kmph. For subarterial road, it is 60 kmph. For collectoral street, it is 50 kmph. And for the local street, it is 30 kmph. There itself, we have written during the classification of payments, during the classification of roads for urban areas. There itself, I have mentioned it. So that is how you fix the design speed from the table given as per IRC, right? So the next geometrical element here is friction. Yeah. Friction is also called as, frictional force can also be called as skid resistance. indicated with the letter capital F. Now, do you require friction on the roads? Is it necessary for our roads? Yes. You require friction for two things. That is for stopping the vehicles when you apply brake or after brake application. And you also require friction to turn your vehicles. So during the turning part of the vehicles, you require friction. To achieve these two things, we use or we require friction. Now, let us consider that your vehicle is traveling in a plain road. Your vehicle is traveling in a plane or a level surface. Let us say the self weight of the vehicle is W and your vehicle is moving in this direction. It's a plain road. Now you have applied your brake. Now, as you have applied your brake, the major force which comes into picture will be friction, and it always acts in the direction opposite to the movement. So your vehicle is moving in this direction, so frictional force will be acting opposite to it. And your tires are being in contact with the road surface, so there will be a normal reaction here. Let us call it as N. Then you have learned it in the mechanics of your first year BTech in civil engineering. Frictional force is equal to coefficient of friction into normal reaction. Coefficient of friction into normal reaction. So this coefficient of friction is indicated with F, and if you write sigma y is equal to 0 for this figure, means summation of all the forces in the vertical direction is equal to 0 for this figure, then upward equal to downward. So your normal reaction will be equal to W. So from this, frictional force is equal to coefficient of friction into self weight of the vehicle, right? So that's an important simple and small formula that can be remembered. Frictional force is equal to coefficient of friction into self weight of the vehicle. Now, this coefficient of friction is of two types. This coefficient of friction is of two types. That is, coefficient of lateral friction and coefficient of longitudinal friction. Right? Both are indicated with the letter F itself. Both are indicated with the same letter. So when should I consider coefficient of longitudinal friction and when should I consider coefficient of lateral friction? Simple. For example, if this is the road and this is how the vehicles are moving on the particular road. So if the vehicles are moving in this fashion, this direction becomes the longitudinal direction for the road, and this is a lateral direction for the road. So if you consider the coefficient of friction, when the vehicle is moving in the longitudinal direction, it is called as coefficient of longitudinal friction. And if you consider the friction when your vehicle is moving in the lateral direction, it is called as coefficient of lateral friction. So this is basically when the vehicle is moving straight along the road. So this is basically when the vehicle is moving in the lateral direction, and there will be a lateral movement of the vehicle involved during the curves, moving at the curves. So at the curves, we generally provide or we generally design for super elevation, extra winding, transition curves, etc. And during the straight paths, we generally design side distances. So basically, in the side distances part, we should use coefficient of longitudinal friction. At the curves, we go for coefficient of lateral friction. Now, this value varies from 0.35 to 0.4, whereas coefficient of lateral friction is again a very important simple 1 mark bit asked many times. It is 0.15. Coefficient of lateral friction is 0.15, whereas coefficient of longitudinal friction is 0.35 to 0.4. And this value varies from 0.35 to 0.4 is based on the speeds. So design speed and F value. So 20 to 30 kmph, design speed is in kmph. 40 kmph, 50 kmph, 60 kmph, 65 kmph, 80 kmph, and 100 kmph. So it is as usual. So it is 0.4, 0.38, 0.37, 0.36, the same 0.36 here, and 0.35 and 0.35. So from this table, you can get the value of coefficient of longitudinal friction, right? So you can note it down these things.